fluid mechanics, fluid dynamics. So first, let's define what a fluid is. Contrary to what you may already be thinking, a fluid is a liquid or a gas. So we are in AP Physics 2 going to largely far and beyond going to be dealing with fluids that are incompressible. Those will largely be liquids in this case. It means that if a liquid is incompressible, it means the density of the liquid can't change. It means it can't change. When it's compressible, the density can change, okay? And like I said before, it's very rare to see a question asked about compressible fluids. If it does come up, it'll be on an MCQ, and it'll have to do with a single equation that is not on your reference table, but if you know the equation, it's going to be very easy, okay? So, moving on from there, let's get into some of the meat and potatoes of what's going on here. First of all, when we're considering fluids, we usually consider them in reference to water. Okay? The significance of water is that water is a fluid that is negligibly compressible, and water has a density of 1,000 kilograms per cubic meter. You want to memorize that number. Water has a density of 1,000 kilograms per cubic meter. It's a pretty easy number to memorize. Do it. So a bit of notation. In the physics realm, density is represented by the letter rho. Looks like a P, but it's a Greek letter, rho. As I've said in previous videos, it's important for your score and for the grader that you are able to differentiate between your English letters and your Greek letters. The strategy here is to always exaggerate the differences, okay? If I were to write the letter rho as I see it on the reference table, they would look exactly the same. So the way I write letter rho is I do like a little curve, and I do that. It's a very curvy P. We're going to be dealing with a quantity known as specific gravity. Specific gravity equals the density, rho, of the fluid that we're dealing with divided by the density of water. Such that if I have mercury, which is a liquid, it's going to have a specific gravity of 13.2. What does that tell me? It means that mercury is 13.2 times denser than water. So therefore, using that information, I can say that the density of mercury is 13,200 kilograms per meter cubed, because I memorized that number. Now, the first really big topic we're going to see in the fluids unit is the concept of pressure, okay? And for those of us coming from mechanics, or virtually any class, pressure might be a little difficult for us to visualize. We can think of pressure, we can think of me applying pressure to the board, but sometimes it's going to be a little difficult for us to distinguish between pressure and force, okay? The first step is to obviously consult the equation. Pressure, P, you see why this is important now? I don't want to be a grader grading your AP exam, and I don't want to be scratching my head wondering if you meant pressure or density. Pressure equals force divided by area. Now, there's an interesting implication in this equation. Given that this is an equation that does not require any calculus, it doesn't involve any vectors, it stipulates that not only is pressure equal to force divided by area, but pressure is equal everywhere. So let's take the classic example of a canister, not closed at the top, filled with water. When we're looking at the area in this equation, we are concerned with the entire area that our fluid is touching. That would mean that the entire surface area of the canister, that would mean the base of the canister and the cylindrical walls of the canister would be the surface area of the canister. That would be our area in our equation here, okay? So in order to calculate the surface area of a canister, you would calculate the area of the bottom, which would be a sphere. That would be area equals pi r squared, where r is the radius of the cylinder or the canister, and the surface area of the walls of the canister would be 2 pi r h, where h in this case would be the height of the water. Okay, so we would add those two areas together to get our total area that the fluid is touching. The force in this case, let's see, what would be the force that causes the water to push down on the base of the cylinder? What force causes me to push down on the ground? The gravitational force. So in this case, our force would be our gravitational force. That means that the pressure here is going to be the same as the pressure felt here, regardless of the point you have on the bottom of the cylinder, okay? As we move further up the cylinder, our pressure decreases. Why is that? Because the force of gravity decreases. Remember, force of gravity equals mg. As we move further up the cylinder, now there is less mass in this area, which means the force of gravity will be less. So it's easier to think of that the pressure of a fluid system is exactly equal at every point at the same height, okay? Meaning that every point at the same height in a system feels the same pressure, okay? Because if every point did not feel the same pressure, a pressure imbalance would cause the flow of a fluid, okay? So another great example of pressure can be seen with the half donut pipe. So let's say I have some amount of fluid present in the pipe. The pressure felt at each height level in the pipe is the same by Pascal's principle that I just illustrated for you. Okay. Now, what's also another important thing to realize about pressure is that there are multiple types of pressure. There's pressure that we apply to a system. There's atmospheric pressure, okay? Atmospheric pressure is 1 atmosphere, as you might have guessed. An atmosphere is a unit of pressure. In the Physics 2 course, the unit of pressure is going to be the standard unit, the Pascal. 1 Pascal is 1 Newton per meter squared. And a Newton is a kilogram meter per second squared. Therefore, a Pascal is the same as a kilogram per meter second squared. Every height has the same pressure. An interesting way to illustrate that is if I were to take a piston that pushes down on this end of the pipe, that piston would apply a force, it would apply a pressure. And like I said before, if there's a pressure imbalance, there will be a movement of fluid in order to equalize that pressure imbalance. So if I apply a pressure downward on this end of the pipe will begin to rise up. We have the equation for pressure, P equals rho GH. And I'm going to try and derive that out for you. The pressure applied by the piston, P, is obviously the force applied by the piston divided by the area through which it is applied upon. And since that piston causes the water to push down, let's say our new level of water with the piston pushing down on it has gone a distance h further down. Okay, and since water has been pushed, we need to calculate the volume of water that has been pushed down. Okay, let's say that the radius of this tube here is little r, and the radius of this tube here is big R. You would say that the volume of water displaced by the piston is equal to pi little r squared times the h, the height of water displaced. And so, since mass is conserved, and in the case of constant density, volume is conserved, that means that the volume of water displaced here must be the volume of water that appeared here, because it flowed through, right? So the volume displaced has to equal the increase in water here, which let's call it increased a distance y. So now our new water level would be up here. So let's use Pascal's principle again to say that since our water level on this side is here with the piston is now at the same level as this water here, we know that this distance is now h plus y. We can say that the pressure at this point, pressure on the left, is equal to pressure on the right. We can say that the force on the left divided by the area on the left equals the force on the right divided by the area on the right. What is the force on the right? The force on the right is the gravitational force. The force on the left is the force applied by the piston. So we know that the gravitational force, Fg, equals mg. So the force on the right is equal to mass times gravity. But we don't know the mass of fluid. We only know the volume of fluid. But we know through our density equation that rho, sorry, I wrote a big D for density, it's rho equals mass divided by volume, okay? So we can write mass as density times volume. So in this case, the gravitational force can be rewritten as rho Vg. And since rho Vg is our gravitational force here, we are dividing by the area through which that gravitational force is applied. So we get a volume divided by an area, and that gives us a linear distance h, or let me use a different variable, z. So we can say that the pressure on the left is equal to the density of the fluid times our height, z, times the gravitational constant, g. Okay? The pressure applied on the left is equal to the density of the fluid times the distance it is submerged, z, times the gravitational constant, g. This whole distance being z. Let's go through that again, just so that we're all clear. The force of gravity applied by this water is mg. M can be rewritten as rho v. So now our force of gravity is rho vg. Since pressure is force divided by area, v over a becomes a linear distance z. So we get pressure equals rho zg, or as it's written in your equation sheet, z is not the variable they use for height, they use h for height. So that's the derivation of your pressure equation. And this is what we call hydrostatic pressure. Hydrostatic pressure being the pressure applied by the fluid. On the left, we have an external force applying a pressure to the system. But on the right, there's no external force applying pressure to the system. In fact, it is the water above the reference point which is applying the pressure to the system. Now that we're on the topic of hydrostatic pressure, we can take a look at the pressure applied by a fluid to an object in a column or a cylinder. Okay, so we have some amount of fluid in this bottle, and we have a item submerged in it. Okay, let's call it a rectangle. A rectangular prism, three-dimensional shape. And let's say, what are the forces acting on this rectangle? There is some water above it, meaning that we have a downward force from the water above the cube. Call that F1. Like I said before in Pascal's principle, pressure is felt everywhere in the system. Therefore, that the water above the bottom of the rectangle is pushing up on the rectangle. So at every facet, every point on the rectangle, there is a pressure pushing on it. On the sides, there is a pressure pushing on the rectangle. But since the forces pushing on the sides of the rectangular prism are acting at the exact same depth, those two forces cancel out. Okay? However, the forces acting on the top of the rectangular prism and the bottom are not acting on the same depth. So therefore, one is not able to cancel out the other. Okay? Which one of these forces acts at a greater depth? That would be force 2, meaning force 2 is greater than force 1. Of course, these are only considering the forces applied by the hydrostatic pressure, meaning the pressure of the fluid. How do we calculate force 2 and force 1 for that matter? we calculate the hydrostatic pressure, we multiply it by our area that it is applied at, and we get our applied force. Okay? Force 1. If we know that the tip of the block is submerged a distance h below the surface, then we can say that F1 is applied through rho, which is the density of the fluid, times height, times g, which gives us the pressure, P, by this equation, multiplied by the area that is acting upon it. And let's say that the rectangular prism has a distance h and a side length r, okay? Such that our area is r squared. Sorry, this distance is y, this distance of being submerged is h, okay? So it's the distance submerged times the area applied r squared, because the pressure is being applied to this area on top right there. Force number 2 is being applied through the same area, r squared, because the same area is present on either side of the rectangular prism, times the pressure, which would be rho times h plus y times g. So if I were to rewrite this as force 2 equals r squared times g times rho times h plus y, and F1 equals r squared g rho h, I would see that the F2 term contains all the terms of the F1 term plus this y, okay? So if I were to distribute that all out, I would get that F2 equals r squared g rho h plus r squared g rho y. So my r squared g rho h and my r squared g rho h both cancel out, and I'm left with my net force, which is r squared g rho y. So the net force is always pushing up on the device, okay? And notice here that y is not the distance from our point to the top of the fluid. Our distance y is merely the length of the object. And since we have here r squared times y, r squared y is the same as the volume of our object. So we can rewrite that the net force is equal to rho vg. In the great words of my friend Sal Khan, I could make a Roe v. Wade joke right here, but I probably shouldn't do that. So let's do an example with the items that we've just learned here, okay? A very famous example is the example of the barometer. Let's explain how that works. The setup is like this. You have a deep bowl, a deep dish, that's open to the air at the top, and connected to that dish is a little glass ampule that stretches up like this, okay? And as it is attached to the bottom of the bowl, it's attached to the bottom of the bowl with like pegs so that fluid can flow through, in and out, okay? So that is what you need to know about our setup thus far. And our fluid, let's say we have water inside the bowl. Now, this is what our bowl would look like in a vacuum, okay? Why is that specific? Why is that important? Because in a vacuum, there is no atmospheric pressure. Being that this is in a vacuum, pressure is equalized because the pressure being applied here is the same as the pressure being applied here. There's no atmosphere here, there's no atmosphere here, so the pressure applied everywhere is the same, which is 0. Now, if I leave inside this ampule as being a vacuum, I'm going to call it V, so leave it there as a vacuum, but I were to take this apparatus and I were to put it on Earth with a pressure of 1 atmosphere, now all of a sudden there is a pressure pushing down on the fluid that is exposed to the atmosphere, Meanwhile, there is still a vacuum inside the ampule, so we've got a pressure difference. Now that needs to become equalized. The pressure is going to push this down, and the lack of pressure here is going to allow it to come up. Okay? And the purpose of this question is for you to determine what height above the original water level will the fluid rise in the ampule. So you are given the density of water, rho, equals 1,000 kilograms per meter cubed. You are trying to find the height that this rises, h. You don't know that. You're given the pressure applied to the outside of the apparatus is going to be 1 atmosphere. Now I'm going to convert atmospheres to pascals really quick so we can work in the correct units, because otherwise our equations don't work. So 1 atmosphere equals 101,000 pascals. Go find out what h is. So the central realization that we need to make in order to solve this problem is we need to remember Pascal's principle. We need to remember at any height, any y value in the apparatus, the pressure must be exactly the same. Which means if we have 101,000 pascals, I'm just going to call it 101,000 to make our math easier. If we have 101,000 pascals pushing down on this part of the apparatus, we need to have 101,000 pascals pushing down on this end of the apparatus. So, since there is a vacuum here, the only item that can apply a pressure inside the ampule is hydrostatic pressure, such that the water level must rise high in order for it to apply a hydrostatic pressure down at this point, at the water level in the rest of the apparatus. Okay? So we say that our outside pressure, which is going to be 101,000 pascals, has to equal the hydrostatic pressure inside of the ampule. We pull our equation from our reference table that pressure equals rho gh. We know that the density of water, because we memorized it and it's given to us in this case, is going to be 1,000 kilograms per meter cubed. We know gravitational constant can be rounded to 10, and therefore we're left with h. 101,000 divided by 1,000 equals 101 equals 10h. So therefore 10.1 is our height in meters. And our answer would be that the height of the water in the barometer would be 10.1 meters. Now, that's correct. We did the problem correctly, but let's take a moment back and consider the practicality of this. If we built a barometer in which, at normal atmospheric conditions, the water would rise 10 meters, that's like the height of my house. We need to find a barometer that can measure pressure on a much smaller scale. Okay, how do we do that? Well, let's consult our equation again. We want to decrease h. So in order to decrease h, we need to increase one of these two values. We can't increase g because we're on Earth and we can't really change that we're on Earth. So the only other factor that we can change is we need to increase rho. We need to increase the density of our fluid. Hey, remember earlier that mercury has a density that is 13.2 times that of water? That is why your barometers use mercury, because mercury is extremely dense. And in this case, we would be working on a distance, not 10.1 meters, but 10.1 divided by 13.2. We would be working on a distance of 0.77 meters. So that's how the density of your fluid can affect your answer, okay? Now, let's move on to buoyancy, which is a lot easier to understand once we draw a free body diagram. So I left this equation on the board, and you're going to see why that's important in just a moment. But first, let's take a little backtrack to specific gravity. Like I said, is a ratio, and since it's a ratio, it has no units, okay? But the importance of specific gravity is if the specific gravity is greater than 1, then our object is not buoyant in water. So if I were to have a canister of water here, and I were to have a block that has specific gravity 1.2, that block would sink to the ground, okay? Because the specific gravity is greater than 1. Now, the specific gravity is the ratio of the density of the object to the density of the fluid, okay? We can change the fluid. For example, I could have a canister of mercury with density 13.2. And if my block were to, again, have specific gravity of 1.2 relative to water, then it would float in mercury. How about this? If my specific gravity is 1.2 relative to water, I want you to calculate my specific gravity relative to mercury. 1.2 equals density of the block divided by density of water, which is 1,000. Therefore, density of the block equals 1.2 thousand. And if we were to divide that by density of mercury, which is 13.2 thousand, our specific heat, specific gravity of the block in mercury would end up being, let's bring out the calculator and do the calculation. Did I do that right? Yeah, I did that right. Specific gravity would be 0.091. Okay, and that's the other end of the spectrum. If your specific gravity is less than 1, you're buoyant in the fluid. Okay, but more than that, not only are you buoyant in the fluid, the specific gravity tells you what percentage of the object must be submerged in order for you to be buoyant. Okay, so you remember how we convert a decimal to a percent? We multiply by 100, such that 9.1% of our block must be submerged in the mercury in order to achieve buoyance. And that's where this equation comes back in. The net hydrostatic force being applied to our block is equivalent to the buoyant force. F sub B equals rho Vg. The buoyant force applied to any object submerged in a fluid is equal to, stay with me here, the density of the fluid times the volume of the object. Okay, don't get those two confused. I see a lot of kids doing density of fluid, volume of fluid. I see a lot of kids doing density of object, volume of object. No, it is the density of the fluid times the volume of the object. So, and this is how you determine if something is buoyant. If something is buoyant, then the buoyant force is greater than the gravitational force. Okay? Remember, our buoyant force is equal to rho Vg, and our gravitational force is equal to mg. So, if we were to turn this into a ratio, the buoyant force divided by the gravitational force, if we want a buoyant force to be greater than gravitational force, must be greater than 1. So rho Vg over mg must be greater than 1. G's cancel out. Rho times v over m must be greater than 1. Remember, rho being density of the fluid, v being volume of the object, and m being mass of the object. Here's the magic part here. If the density of the fluid is, let's say, 13.2, and the volume of the object is 1 cubic meter, the density of our object is 1.2, and the volume of our object is 1 cubic meter, then we have greater than 1. Okay, now what did I do here? This isn't mass. Oh, but it is. Because the density of our object times the volume of our object equals mass of our object because of the density equation. Rho equals mass divided by volume, okay? So this can be rewritten as density of the fluid times volume of the object over density of the object times volume of the object equals 1. These begin to cancel out, and then we say that the density of the fluid divided by the density of the object must be greater than 1. And if we were to take the reciprocal of that. Density of the object divided by density of the fluid must be less than 1. And this perfectly agrees with what I told you earlier. Remember what I told you earlier, that specific gravity is equal to the density of the object over the density of the fluid. If this is less than 1, the object is buoyant. Before we delve into the last part of the fluid dynamics unit, let's go over what's on your reference table. Hydrostatic pressure. Pressure equals rho GH on your reference table. Density, rho equals m over v, is on your reference table. Pressure equals F over A is on your reference table. Now, the way it's written on your reference table is pressure equals pressure naught plus rho GH. So let me explain what this means. Pressure equals rho GH is the hydrostatic pressure. It means the pressure from the water or fluid above you. P naught is the pressure of the environment, okay? Meaning that the total pressure of an object at this point is the pressure applied by the fluid above the point, in addition to the pressure applied by the atmosphere, because there is atmospheric pressure. That is what P naught is. P naught is your atmospheric pressure. In the case of a vacuum, P naught disappears. That's all you need to understand there. Your buoyant force equation, meaning that the buoyant force, F sub B, equals rho Vg, that's on your reference table. Now, if you're following along on your reference table, which you should be, the next two equations are going to be the equations we're covering right now, okay? And that will be the flow rate equation, A1 V1 equals A2 V2. Let's jump into that right now. This is my pipe. There's a fluid flowing through the pipe. All this equation is telling me, very simple to understand, means that the area, cross-sectional area, if you don't know what cross-sectional area means, it means that if I sliced this tube right this way, as in I am cutting it perpendicular to the flow of water, the area of the surface I would see right here, it would look like this. If I were looking straight at the pipe, the area of what I'm looking at is the cross-sectional area. That is the area I'm looking at in this equation. It means the two-dimensional area here is A1, two-dimensional area here is going to be A2. The velocity of the fluid is going to be V1. This is my point 1, this is my point 2. The velocity of the fluid here is going to be V2. I should write these smaller. Big V is volume, little v is velocity. So simple equation. If I'm given 3, I solve for the 4th. And it's effectively a statement of conservation of mass, okay? Meaning that if I'm in a smaller, more constricted cross-sectional area, more mass must be flowing through than if I am in a much wider cross-sectional area, the velocity must be smaller. Think of it like if I am putting fluid through a funnel. Okay, let's say I'm filling up my water bottle and I've got a funnel on top. You'll notice that as you pour water into the funnel, the rate at which water flows through the bottom of the funnel is much faster than the rate at which water is decreasing at the top. The water is flowing through at the top. So that's all this equation tells us. Next equation, brace yourselves, is I need the reference table to copy this down. That's the good news, that this is on your reference table. It says P1 plus rho Gy1 plus 1/2 rho V1 squared equals P2 plus rho Gy2 plus 1/2 rho V2 squared. So let's discuss what this means. So this equation is, let's talk about what it's telling us, because it's a lot easier to understand an equation if you approach it by what it's trying to model. This is a conservation of energy equation. Pressure, as we know, if you have a pressurized tank of oxygen and you release the valve, oxygen is going to come rushing out, okay? And it's going to come rushing out with some kinetic energy. Therefore, the pressure stored in the oxygen tank at very high pressure is a type of stored energy, okay? So we're going to call this term the energy from pressure, all right? This term, rho gy, if we multiply that by the volume of fluid that we're dealing with, we get rho times volume equals mass. We get mgy, which is the potential energy equation we learned about back in Physics 1. So we have pressure potential energy, gravitational potential energy, and 1/2 rho v squared. We multiply by volume again, we get 1/2 mv squared, which is the kinetic energy. So U sub g, U sub pressure, and Ke. It's a conservation of energy equation. That is all it's telling us. It says that the sum of all of the energy at some point 1 must equal the sum of all the energy at some point 2. And from there, now that we understand that, we can apply it. The classic example how we apply this equation is in the case of a water tower. So if I draw a big old water tower, and let's say that the water tower has punctured a hole right there. You can see the small little hole, okay? We're going to give you that atmospheric pressure, P0, equals 100,000 pascals. We're going to give you that the height of the water in the tank relative to the bottom of the tank is 10 meters. We're going to say that the height of the hole relative to the tank, the height of the center of the hole relative to the tank is 1 meter. We're going to tell you that rate at which the water level is falling, meaning the rate at which the water level is falling, we're going to say that that rate is negligible. So this rate is 0. Our job from there is we're going to need the density of the fluid, let's call it 1,000 kilograms per meter cubed, because this is a water tower and it's going to be holding water. And now what you need to find is the velocity at which the water exits the water tower. And it's going to come out like that. What is its initial velocity as it exits the water tower? So this is a continuity equation. Point 1, we're going to define as at the top. Point 2, we're going to define as at this little hole right here, okay? Now, I know this doesn't look like a pipe, but you can model it as such. You have a big pipe here that has some cross-sectional area like that's the big end of the pipe, and you have a smaller end of the pipe that is this little hole in the water tower. So water is effectively flowing this way like it would in a pipe. So this is going to be our point 1, this is going to be our point 2. At point 1, what's our pressure? It's going to be atmospheric pressure. P1 equals P0. We know our density, we know our gravitational constant, Y1. Well, we know the height of the water here, but it would be useful for us to, as we do in our other physics classes, redefine our scale. If this is at height 10 and this is at height 1, we can redefine the scale to say that this is at height 0 and this is at height 9. So our Y1 is going to be 9. 1/2 rho V1 squared. We said that the velocity at which water is, the height of the water is decreasing is negligible. Therefore, V1 is approximately 0. Therefore, this whole term goes to 0. And we said that we were going to redefine our scale to say that y2, the height 2, is 0. Therefore, since y2 is 0, this whole term can go to 0. So at P2, the P2 is just going to be our atmospheric pressure because P2 is exposed to the atmosphere. Okay, so if we plug in everything now, we get P1, which is P0, plus rho g times 9, plus, not plus, equals P2, which is also P0, plus 1/2 rho V2 squared. P0 present on both sides, that can cancel out. We get rho g times 9 equals 1/2 rho V2 squared. Our rho's cancel out. We get 2g times 9 equals V2 squared. G is 10, so we get 20 times 9 would be 180 equals V2 squared, and rad 180 equals V2. And that's how we find the velocity at which water exits that little hole. Thank you guys so much for watching. As always, enjoy life.